Welcome to the next lecture on stellar evolution. As we continue to study stars, we talked about those internal processes that happen within our sun, looking at some of the solar activity. We talked about how we classify stars, but today we're actually going to start looking at how those stars change over time. So we're going to look first at something that we've already talked about. We're going to look at star birth. So looking at that solar nebular hypothesis, where this would really occur, the types of star populations that are available, as well as how stars form in clusters. And we're also going to look at how the amount of mass actually influences the star's birth, life, and even death sequence. We're then also going to start going into how the core structure is changing, as well as what are some of the after effects as a star is dying off and it's a low mass star. So the first thing is we have to look at the interstellar media. As we gaze out into the night sky, not every object that we observe is a star. In fact, quite a few of these objects are very large gaseous regions that we call nebula. And these nebula regions have lots of dense gas pockets, and as gas is getting very close together, it's gathering in mass, eventually it collapses and it starts creating a protostar and a protoplanetary disk. This is where we get to see that solar nebular hypothesis really taking place. So when we observe these types of nebula, what we see is that there are three different types of categories. We have emission nebula, we have dark nebula, and we also have a reflection nebula. So looking at our emission nebula first, if we look at, say, a nebula like the Great Nebula in Orion, or also known as Orion's Nebula, this is a beautiful emission nebula. It has very vivid colors all throughout different pockets, but the most prominent regions that are very, very bright are actually gases that are being ionized from very hot stars that were formed within the gas cloud structure. Now, what we're seeing with an emission nebula is, again, those gases are ionized and they will emit the light. Because they are very hot, they are going to radiate their own light. So we can observe these spectra, and we get a spectra very much like the one that's pictured below, where we see the different types of emission of hydrogen, helium, primarily, and then other elements as necessary. For dark nebula, this is actually quite the opposite. So what we get to see in a dark nebula is really not much. It's dark. It's an extremely dense pocket of gas. And because of how dense the gas is, light from stars that may have already formed within the dark nebula have not cleared away enough gas yet to allow their light to actually be seen. So for dark nebula, we can try to see as much as we can, but we do believe that there is a lot of star formation that is occurring within this actual structure. Because it is dark, it is not emitting light, and we believe that it's going to be very cold gas in general because it is not being warmed by stars nearby. If we look at a reflection nebula is going to be a nebula where the gases are being, if you will, a little bit ionized to the point where they are reflecting light off of nearby stars. So as you're starting to see light from a nearby star or even a small cluster of stars, this area that is very highly concentrated gas will collect the light and reflect it back out. Now, reflection nebula often have regions that are also very dense, and we cannot necessarily see into those extremely dense structures. But again, because of all the gas and dust, most likely it has the right kind of conditions for a lot of star formation inside those gas clouds. Now, going through that whole solar nebular hypothesis, you have your gas clouds condensing down, you get a protostar, protoplanetary disk. The protostar is collecting mass as it is essentially growing. Now, once that protostar reaches a critical mass, it will start the process of thermonuclear fusion at the center, so at its core. When thermonuclear fusion occurs, the radiative pressure from the core pushes out, and it actually sends out the first solar wind from that star. That solar wind is actually pushing away all the gas and dust and smaller objects. And so what we get to see is that the Tatari wind is the initial wind that allows us to see that this star has reached the main sequence. Now, stars will also go through their stellar evolution cycle, or their stellar birth, if you will, from different types of shock waves that may occur. So stars will, as they go older, they will lose their outer layers. And if they're very low mass stars, the outer layers will just drift away. But more powerful, much larger explosions, much larger shock waves rather, from supernova, much higher mass stars, will actually ripple out with a lot of energy, a lot of force because of all the material there. And it will strike into these larger gas cloud structures. Well, condensing gas because of a shock wave causes rapid star formation. And so that may actually help not only give heavier materials to that gas cloud from the supernova, which is a dead star, but it may also help with the formation of that star system to be a bit more rapid than what it should have already been. So as star birth is taking place, what we're seeing within these nebular structures is that the gas clouds are very large structures. They may be tens, even hundreds, maybe even thousands of light years across in distance, and that's a lot of gas. Stars will form all throughout, so they often form in groups called clusters, and there are two major types of clusters, both open and globular. An open cluster is going to be just what it sounds like, a very loose connection of stars that are gravitationally bound to each other. A globular cluster is pretty much what it sounds like as well. It's where you have hundreds of stars very closely connected to each other, and they appear to be more in a spherical shape as a group. So very dense towards the center of this sphere and a little bit loose as you're getting further from that center. So these are globular clusters. Very large structures often. Now, as we're seeing stars form within nebula, not all the stars will form exactly the same, nor will they form at the same time, because of the different types of masses as well as the different types of chemicals that are distributed within these atomic cloud structures. So if we're trying to look at the different types of stars and really understand what it is we're observing, we have to start looking at the different classifications of stars. We have two different types of populations. The first population, a population 1 star, is going to be a relatively new star. It's fairly young, and it is going to be very heavy, meaning it has a lot of heavy metals or heavy materials mixed into its spectra. If we're looking at a population 2 star by comparison, it's just the opposite. It's much older, and this particular star is going to be fairly light in terms of its spectra. It won't have a whole lot of metals within its overall wavelengths as you're observing. Now, what's really necessary to understand here is that as we're observing the different types of stars, we can see population 1 stars or population 2 stars often in groups. So we may identify a group of stars that are metal rich, and those will be population 1. We may also find a cluster that is going to be population 2 mostly, and those population 2 stars are going to be much older, indicating that this cluster is a very old star cluster. Now, as we're looking at those different cluster types, the open clusters, again, are very widely distributed. And so they have no true shape necessarily. And oftentimes, open clusters are very small. They have generally fewer than 100 stars, most are usually under maybe about 50 stars, and they're gravitationally bound to each other. Open clusters from our observations tend to be much younger population 1 stars. And so you can see an example of an open cluster in the beehive cluster pictured over to the side. You can also see an example of a globular cluster. The globular cluster has kind of that spherical looking shape to it. And as you start looking at the center, it's very dense. As you start moving away from the center, it becomes less dense. What you're observing in a globular cluster are generally those population 2 stars, which are much older, indicating that this cluster has been in existence for a very long time. Now, if we start considering all the gases within a nebula structure, and it's condensing down, the amount of mass will actually determine how quickly the star will form. So if we're looking at a star much like our sun, which is 1 solar mass, that 1 solar mass would probably condense over about 1,000,000 years, give or take, maybe longer, in which time you're condensing your gases together, creating a protostar, and then eventually creating a star. Once that star is created, you're now on the main sequence. Let's say by comparison you're looking at a star that is maybe about 15 times the solar mass, so 15 times the mass of our sun. That star may actually condense in a much quicker fashion, and it may only take about 100,000 years, going from gas cloud to main sequence star. That is a very rapid star formation. And so when you have rapid star formation, you get a very large mass star. If you have a much more gradual star formation, meaning it takes much longer, your star tends to be much lighter by mass. So we use this relationship to look at different types of clusters. Below, we actually have 2 clusters that are pictured. The cluster on the left is what we call the Pleiades cluster. It is a beautiful open cluster. We can see nebulosity, so we can see some of the excess gas that was left over from the nebula that is not having any kind of star formation, but it is in fact showing us a lot of the reflection from very hot class O, class B stars. And so this is actually a visual image you can see through any kind of telescope, but especially a high-powered telescope, this kind of cluster. It's very beautiful. Now, looking at the HR diagram for this cluster, we try to determine the existence of stars that are still being formed. And what we see is that this cluster is old enough that all the stars that are being formed are really formed at this point. Very few are still trying to reach the main sequence. Now, when we're looking at the star clusters, some of the stars have also left the main sequence. So that's indicating that those stars formed a little bit before the others. So again, these stars are not forming at exactly the same rate. If we look at the Monoceros cluster, this is a cluster that is located inside of the constellation Monoceros. What we can see in infrared is that there's a lot of gas and dust mixed in, and as a result, because of all the gas and dust that still exists, we see a lot of star formation that is still occurring. And a lot of the star formation is gradual, but some of it is still pretty rapid, indicating that there are going to be some high mass stars here, but the majority are low mass stars, and most of them will be within a very close range to our sun. Now, if we're looking at the main sequence stars in general, these are stars with 0.4 solar masses or more, so 40% of the mass of our sun or more. These types of stars will start off and they have a lot of hydrogen at their core. They have some helium as well. The hydrogen will start off in fusion when that star has reached critical mass. the hydrogen at the core over time will actually start to deplete. And so initially, our star by mass would have about 74% hydrogen, about 25% helium, 1% of everything else. The 74% hydrogen over time is being consumed. And so what we're seeing is the core of our sun is actually depleting to about 25% leftover hydrogen today. So we're seeing a massive change, but that makes sense. For a star to continue sustaining the radiative pressure against the gravitational in-pull of all the mass that's on its layers, what has to happen is that the star has to have a process inside, which is fusion, that pushes out, and that's that radiative pressure. So the mass inside of the star chemically is changing. Now, if we look at our sun specifically, since it is the closest star to us, we can see that this change over time, as you start getting heavier materials at the core, actually increases the size of the star. So from when our star first formed to now, our star has actually grown radially, so physically, about 6%. Its surface temperature, likewise, would have gotten a little bit warmer. We say that originally the sun was about 5,500 Kelvin. By today, it's about 5,800 Kelvin, so a little warmer. We also see that the luminosity has increased by almost 40%. That is huge. So you're increasing your radial size as the core gets more heavy elements in it. As that sun got bigger, it got hotter, and it got more energy output because there's more surface area, so that makes sense. Now, if a star has less than 40% of the mass of our own sun, so a 0.4 solar mass or less, this is going to be a class M star. So it's going to be a red dwarf. It's very small and it's very cool. What we're seeing as a process at this smaller star internally is that hydrogen is distributed all throughout the star, including the core. It is sustaining fusion at the core. However, because of the size of the star and the relatively low mass, the hydrogen, once it has fused, is actually cycled out because it's very hot. So heat rises in the convection cycle, and it does not have enough radiative pressure to keep the convection cycles away. So heavy materials are then cycled out because of the fusion, which means the lighter hydrogen that was not originally in the core can be cycled into the star. Now, as you're going through this process of cycling heavy out, light in, what you're able to do is use almost 100% of the star's mass, unlike a star that is much heavier, because the radiative pressure is keeping the convection cycles away from the core. But a red dwarf like what's pictured is actually allowing all of that material to be cycled. That's really cool. So if we try to consider the relationship with mass in terms of the stellar evolution going from gas cloud into the actual star, we can see that the mass will determine either rapid or gradual formation. The more mass you have, the more rapid; the less mass, the more gradual. Well, the same kind of relationship still plays as the star reaches the main sequence. So a more massive star on the main sequence will actually have a shorter lifetime in general, and a less massive star will have a much longer lifetime. So this mass relationship still plays. For example, if we look at a mass of about 25 times the mass of our sun, so 25 solar masses, this particular star, being a class O star, very hot, very luminous, very large, would only have a life expectancy on the main sequence of about 4 million years. Now to us, that sounds like a very long time, but to a star, that is very short. By comparison, our star is a class G star. It has one solar mass. has one luminosity because our luminosity scale is based off of our own sun. Our life expectancy on the main sequence for our star is about 12 billion years. Billion with a B. That is a much longer lifetime. But let's say we're looking at a red dwarf star, class M. It is going to be about half a solar mass, and it's really going to have a very long lifetime because we're looking at about 700,000 million years. That's an extremely long lifetime. 700,000 million years, or about 700 billion. That is extremely long. Now, you have to consider something here. If you're looking at the entire age of the universe, I know we haven't talked about it as a broad topic yet, but I'm sure you've had some exposure at some point. The age of the universe, as we currently clock it, is about 13 to 14 billion years old. So these old stars that are class M are still very young. They're very, very young. In fact, they're so young that they could actually watch the entire universe go through its aging process, and depending on which theory you're following, they may not fully be extinct when the universe has finally reached to the point where it is either completely cooled off or collapsing again. So that is very crazy to think about, that these stars that are class M stars are very old, they're cold relative to other stars, but at the same time they can last much longer than these really hot stars that are much more massive. Now, as we start seeing this core structure changing due to the different types of fusion that are going to occur, starting off with hydrogen fusion, what we see is that the sun will actually expand very rapidly. And by comparison to other stars, the more massive you have for a star, the larger that star will be radially, so physically. Now, if we're looking in terms of, say, our sun and Betelgeuse, just by comparison, Betelgeuse is a very old star, it's a very heavy star, and it's going to be really, really big because it's getting towards the end of its life. But what we're looking at by comparison, if you can see this diagram, is that the sun is a small itty-bitty white dot. And what we're seeing is that the sun will eventually expand outwards, leaving most of the terrestrial planets either to be completely stripped away, meaning they're consumed by the sun, or they become bare, and they're really very close to the sun at that point. We believe Mercury, Venus will be completely consumed, and we even believe that Earth may become either very close to the sun, to the point where we would be in the solar atmosphere. Eventually that would change our mass relationship. We would probably collide with the sun, making Mars the closest planet to the sun. That's a massive change. That's a lot of distance. That's a very large expansion. Betelgeuse, on the other hand, is far, far larger. Betelgeuse is really about the size of Jupiter's orbit, just about. So by comparison, our sun is very small. Now, when we're looking at the core structure inside of our star, or any star with about 0.4 solar masses or more, what we're seeing is that the star reaching the main sequence from a protostar is going to have a hydrogen fusing core, and then it's going to have radiative pressure pushing those outer layers away. The outer layers can no longer funnel any kind of material into the core once that radiative pressure starts. So as soon as fusion begins, that's it. The star is going to start burning all of its core material, and that is the only fuel source that it has for life. If we're looking at how this star is changing, once the hydrogen has been primarily depleted, it's turning into helium, so it's getting heavier material. The helium being heavier will sink inward towards the core, forming a new core that is all helium, almost all helium. Hydrogen, being a little bit lighter and still fusing, is pushed out away from the helium into what we call a fusing shell. So this would be a hydrogen fusing shell. This is where the star has left the main sequence and it has become a young red giant. Now, as the star continues to get older, what will happen is the hydrogen continues to burn out. It is still fusing in a shell, but the helium will start fusing after it starts a helium flash. At that point, what we're seeing is that the helium in the core is now being used to support the radiative pressure, which sustains the star from collapsing. This is where we have a full-on red giant star. So it is no longer a young red giant, it is instead a red giant star. Now, as the star is getting older, what we're starting to see is that because you're leaving the main sequence, you're going into what we call the red giant branch. So as the star continues to get older, it continues to get larger with more surface area. It's also going to become more luminous. Now its temperature may decrease because you're looking at, say, the sun of 1 solar mass. As it expands, it's still 1 solar mass. That part did not change. What instead is changing is that the size of the star has increased. That is going to change the luminosity because the surface area has changed. It is also going to change the density of the outer layers. And so this star is going to get much larger. It goes into what we call, again, the red giant branch. As the star is starting to use its helium at the core structure, it goes through that helium flash and it starts traveling along what we call the horizontal branch. And the horizontal branch is where the star is going through some changes. It's trying to get hotter, it's trying to get the core more dense, because helium being heavier will require more density and more compression, if you will, so the core has to get smaller. And then as that core is smaller, it is forcing helium to fuse, and likewise radiative pressure is pushing out. So it's still sustaining those lighter, less dense layers that are much larger than the original star. But the star does grow and shrink in size based off of the fuel that it is using. Now, as this star has gotten to the point where it has a lot of its helium being burnt out from the core, the heavier materials formed out of helium fusion are generally carbon and oxygen, and those will sink towards the core. Helium is pushed into a fusion shell around the core. Hydrogen that was left over is also pushed out from the core into a dormant hydrogen fusing shell. Now, the dormant hydrogen fusing shell is not something that is necessarily sustaining fusion. It may have fusion here and there, but it's not sustaining. And there's very little hydrogen at this point to really be used. The helium is actually sustaining the star at this point, and it's being burnt out. The carbon and oxygen is not fusing, and that sits at the dead center of the core. What's happening is that the core again had to shrink. Now the star's core is about the size of a planet, a little bit larger than Earth. But its outer layers have to expand. And when it expands, it goes into the second giant phase, or what we call the asymptotic giant branch. That AGB star gets very large, possibly about Earth's orbit in size. Now, we can see the different types of evidence for how stars are forming, not by watching any one star over its entire lifetime, because that would take much longer than the human civilization has been around, but Instead, we can look at globular clusters to determine the different stages of life for the stars that were once formed and are still living, both on the main sequence and then also at the turnoff points where they go into the other phases of giant, asymptotic giant, and eventually horizontal branch as well. So we can look at other globular clusters to really determine how stars are evolving, and that's where our evidence comes from. Now, the last stage of a low mass star is what we call a planetary nebula. And these are some of the most beautiful objects to observe in the entire universe. These are actually where stars have gotten so large that their outer layers drift away. They just poof off. Because of the low density and the radiative pressure from the internal part of the star, the core, the outer layers are just puffed off of the star, and they lose their gravitational relationships. They're moving away. They're very hot, they're very excited, and as a result, they're gases that are ionized. And so we will see these beautiful, vivid colors of what kind of elements actually exist within that star as it poofs away those outer layers. Now, some stars will actually die off in a planetary nebula that's a little unique. And so what's happening is as the star is getting older, it's expanding. But the core, sorry, not the core, the equator of the star is moving with a little bit more velocity because it's a much larger region now. So what will happen is some of those materials around the equator of the star will poof off into kind of like a torus, or if you will, a donut shape around the star. When the star loses its outer layers into the planetary nebula, the material is fluid, and so it is wanting to find the points of least resistance. And so those materials will poof off and give us beautiful shapes such as the Hourglass Nebula. That's actually a planetary nebula, and what you can see is at the very center of the nebula is the leftover star, which is what we call a white dwarf. Now, these stellar remnants from planetary nebula are absolutely beautiful events, but what's left over, again, is that white dwarf, and that is the stellar core. So it is the core of the dead star. When we're looking at a white dwarf star, they're very hot. They take millions of years to cool down. And as a result of being so hot, they will continue to ionize the gases that are nearby. Now, because we're dealing with a stellar remnant, so a dead star, what we're going to do is compare the core size to a planet. So if we look at Earth, for example, Earth is a very, very small object compared to the Sun. But as you have the core structure of the Sun compressing to get as much as it can out of fusion, the core continues to shrink while the outer layers continue to expand. When those outer layers poof away, the leftover core is about the size of a planet. So it's very, very small. Now, here's the thing. If you have more mass in this star, the more mass you have, the greater the compression of the core, which means the core is much, much smaller. The less mass that you have, the more surface area that core will still have. So it didn't have as much compression because it didn't have as much mass. Now you may be thinking of this and it's kind of like, okay, wait a minute, what's happening? We got expansion, we got shrinking, which is it? It's both. The core shrinks within a star. The outer layers poof away, so they get much larger. As that core has more mass, it compresses even more, so it gets tighter. And so the white dwarf has a maximum mass capacity, what we call the Chandra limit. We say that a white dwarf can only have about 1.4 solar masses. which means a star that is considered to be a low mass that will produce such a star, stellar remnant rather, can only have a certain mass limit as well. So stars will generally, in a planetary nebula, poof away about 40% or more of their mass. So you can actually calculate this backwards and find out the mass of the most massive stellar remnants that are white dwarfs. Now, as we're watching a white dwarf, it makes sense that if you have more surface area, that you're going to cool much more quickly. If you have less surface area, you're going to cool a lot less quickly. And so if you're looking at the white dwarfs in terms of cooling curves, what will happen is a white dwarf that is much smaller in mass will be much larger in surface area. And so it will cool very rapidly. Now, just to recap this entire process, because it's a lot of information, once you've gotten past the solar nebular hypothesis, you reach the main sequence as a star. And so a star, much like our sun, is already main sequence. It is burning hydrogen at its core using thermonuclear fusion. Once that hydrogen as a fuel source has been depleted almost entirely, the helium that's being created as a byproduct of hydrogen fusion is becoming the dominant component of the core. And so that dominant component of the core, being helium, is not fusing at this point, but the star is getting much larger. So it goes into a young red giant phase and then eventually becomes a red giant. The hydrogen in this case is going to be fusing, but it is not going to be the dominant part of the core. The helium is. The core continues to shrink at this point, and then once we get to a critical point in the star's life, the helium goes through what we call a helium flash. That helium flash indicates that the star is now burning helium primarily at the core. Hydrogen is still burning a little bit here and there on the fusion shell. Then, as the core structure is becoming a little bit more predominant in the byproducts of helium fusion, so carbon and oxygen, for example, what we're seeing is that the hydrogen is pushed out once again, helium is pushed into a shell as well, and the carbon and oxygen take over the core. Now, eventually the hydrogen in the fusing shell is no longer really serving to fuse. It does fuse a little bit, but it's what we call dormant. The helium is still serving as the primary source of fusion at this point. The sun is continuing to grow, and eventually, as it gets old enough, those outer layers have poofed so far away that they drift off of the star, leaving the leftover stellar remnant. And then you have no more nuclear fusion at this point, and so the white dwarf stellar remnant is actually just a leftover core object that will continue to cool, and it takes millions of years to cool down. So, I know it's a lot of information, but please, please, please go back, review any type of supplemental materials that I've already provided. Also, make sure you go back and review the notes. Please understand that process of how stars are evolving. This week was very specific to the low mass stars, but the stellar evolution cycle is pretty much the same for even high mass stars, which we'll talk about next time. So review those supplemental materials again. Make sure you're working on that discussion and also the assignment. And if you have any questions whatsoever, please email me.